Okay, you've already done it. Okay. Hi everyone. Welcome back to Make Easy at Academia. So please don't forget to like our videos, share, subscribe so that others too can be able to benefit from this tutorial. So welcome to another episode. We are still in physical chemistry. We are going to talk about another topic today, which is thermochemistry. We have already talked about the gas law before, involving either Charles law, Boyle's law, general gas law, IV gas, Dalton law, partial pressures, and the calculation related to that. So once you subscribe, you'll be able to have an access to the material we are using. So please follow us. Now today we talk about thermochemistry. Thermochemistry. Here we are going to base only calculation aspect. So all the other ones that involve explanations, you will check materials so that you'll be able to get the full concept. So when we have the word thermal itself, when we have thermal, just like physics, when we have thermal simply means heat. That's the meaning of the word thermal. Thermal means heat. So in chemistry, there's one thing that we normally talk about. Let's say we have A plus B to be C plus D here. So whatever we have here is what we call reactant. So what we have here is what we call product. Okay. So because I will talk about a lot of things here, and inshallah, by God's grace, you get a lot of concepts in this area. So now, what we have here is reactant, and at the same time, what we have here is product. What we react together. Just like if I have salt and water, let's say I had salt and water together, and I have salt water. Actually, we have salt water here. So what we had together is the reactant, and what we have is the product. I hope you are following, right? So in this case, we have a way of how we can reverse equations, but we deal with that with mole ratio. Let's say, for example, maybe I have something like A, B, C, and D. The one that we have as capital letters, they are the moles, and they are the main reactant that we add together. The one here is the product. So the mole here, the mole ratio here is the coefficient that we have between them. So this is A here, this is B, this is C, and this is D. So it can be a number. Let's say, for example, I have hydrogen gas plus half of oxygen gas to give H2O. Is it balanced? Let's check. Here we have 2 hydrogen. Here too we have 2 hydrogen. Here I have 1 hydrogen because 1 over 2 times 2, that's going to be 1. And of course here too I also have 1 oxygen. So if I want to write the mole ratio of this one, I can write it as you can see. The number that we have beside this one is just 1. So I can have 1 ratio half, then ratio 1. It's not 2. You see, the whole of this one is water. And do not consider the subscript, we are considering the number beside them. So the number we have beside the given reactant of the product is what we call the moles. I hope you are following, right? So now, in dealing with that, we'll be talking about all these moles here. So in short, this one is divided into 2. We have endothermic reactions. We have endothermic reactions and we have exothermic reactions. So do not be perplexed. I will define all these ones, explain them in details in the materials. So here we are going to base only on the calculation aspect, but still I need to explain some things so that you'll be able to get the concept. So when it is involved in the surrounding, they said exothermic reactions or endothermic is a physical change in which heat is absorbed into the system. If you recall when we were in secondary school, they talk about what we call physical change and chemical change. You remember that? Physical change is a type of change that does not involve any new substance. Nothing change. Like let's say cooking of rice now. If you cook rice, nothing changes, right? Yeah, fine. But if you look at chemical change, is when new substance form, like burning of wood. If you burn a wood, what are you going to have? It will turn to ash. It cannot be reversed back. So that's what we have here. So this one, if you see this, do you know the meaning of this symbol? We call it change, which is delta. Since it is a form of energy, so for this, heat is always positive because it's gaining heat, while this heat is always negative because it's losing heat. So any reaction you see that is positive, that one is endothermic. So if it is negative, that one is exothermic. Those are the concept we are going to talk about here. We have what we call endothermic reactions. At the same time, we have what we call exothermic reactions. So when it is positive, that one is endothermic, and when it is negative, that one is what we have exothermic. I hope you are following me, right? Yeah, fine. So now I will be dealing with all these concepts. I want to be taking them so that you don't get perplexed. So now let's see this. How can we reverse equations? Let's talk about that. How can we reverse equations? So don't forget all this definition related to this. I will give you the materials. So we are going to base only on calculations aspect. So how can we reverse equations? So let's talk about thermochemical equations. Thermochemical equation. Thermochemical equation. And there I will talk about how to reverse equation. How to reverse. So when we have thermochemical equations, it's just a balanced chemical equation showing the physical state of all reactants and products and the enthalpy change of the reaction. We are going to talk about, don't worry, all those definitions will there for you. We have standard enthalpy change, entropy, all those ones. So let's just talk about how to reverse equations. Reversing of equations means that what we have at the reactant will go to the product, and what we have at the product will come back to the reactant, and it's going to affect the energy level of that particular equation. For example, what are we trying to say in essence? Let's say I have A plus B to give C plus D. Let's say I want to reverse this one, for example. So meaning what I have at the product will go to the reactant, and what I have at the reactant will go to the product. How? So that means if I want to reverse that, so that means I will have C plus D. You can see what I have at the product goes to what I have at the reactant, then what I have here too, I will have A plus B. Can you see that? What we have at the reactant goes to the product. What we have at the product goes to reactant. So, and it's going to affect the energy level. If the energy level we have there is endothermic or exothermic, meaning if it is negative, the moment we reverse it, it is going to turn to positive. Or if it is positive, the moment we reverse it, it's going to turn to negative. What are we trying to say in essence? Let's look at this problem. Let's look at this one. They said reverse the following thermochemical equations. Reverse the following thermochemical equation. Reverse the following thermochemical equation. 1, 2 carbon in solid plus hydrogen gas to give tin C2H2. Tin plus 22.6 kilojoule per mole. The second one we have is carbon in solid gives carbon in gas, and that one they said energy level of this is plus 716 kilojoule per mole as well. Then the third one we have is calcium chloride, calcium solid plus chlorine gas, and the energy level of that one too as well is given as plus 794 kilojoule per mole. So look at what we have. We're just trying to create so all these ones are just so simple and straightforward. Look at it. Let's reverse the following thermochemical equation. I told you about the definition of this. You don't need to worry. Check your materials. I only want to base on calculation aspect to save our time. So we have to reverse all this equation one after the other. It's just so simple and straightforward. As I mentioned earlier, to reverse equations, what we have at the product will go to reactant, and what we have at the reactant will go to product. So let's take them. I will solve this and this, and I will leave the total exercise, right? Yeah, fine. So let's take them one after the other. Let's take the first one. They said, you can see what we have at the reactant is this, And what we have at the product is this. So if I want to reverse it now, this will come here and the other one too will go there. So here, that means that we have C2, H2. I think it's supposed to be gas, yeah, it's gas, I think. So now this one too will go here. So that means that we have 2 carbon solid plus hydrogen gas. Can you see that? Now, as I mentioned, it affects the energy level. If it is negative, it will turn to positive. Or if it is positive, it will turn to negative. So now we have minus delta H1 is equal to, now you can see what we have is positive. So the moment you reverse it is going to become negative. So we're going to have minus 22.6 kilojoule per mole. Can you see that? It's just so simple. So now let's try the second one too as well. Let's see the second one. So now you can see this one is carbon, but it's different. What we have is solid, what we have is gas. So let's reverse it. That means that we have carbon, which is gas, then carbon, which is solid. So minus, changing delta 2 is equal to, now this is positive, it's going to turn to negative. We have minus 716 kilojoule per mole as well. So if you look at this one too, like just leave this one same processes. How are we going to do that? This is reactant. To go to product. This is product. To come to reactant, and what we have here we change to negative because we still have positive. So if it is positive, it will change to negative. If it is negative, it will turn to positive. So now let's look at this problem. Let's look at this problem. Let's look at this problem. They said, question 2. When 2 moles hydrogen gas, 1 mole of oxygen gas reacts to give liquid water, 572 kilojoule of it evolved. So they now said, okay, according to these equations, we are given this 2 hydrogen gas plus oxygen gas give 2 water. It's liquid, and they said its energy level is minus 572 kilojoule per mole. So they now said, write this equation for 1 mole of liquid water, give the reverse in which 1 mole of liquid water dissociate into hydrogen and oxygen. You can see this one is much, but it's still simple and straightforward. So let's see how we are going to approach that. Okay, let me hold these materials. Now, they said when 2 mole of hydrogen gas, 1 mole of oxygen gas react to give liquid water 572 kilojoule of heat evolves in these equations. And they said write this equation for 1 mole of liquid water, give the reverse in which 1 mole of liquid water dissociates into hydrogen and oxygen. You can see, let's firstly write the equations. I want to break it down so that you can be able to have better knowledge about that. So let's see how we're going to break it down. So this is what we have. Look at what we have, minus 572 kilojoule per mole. This is what we have from the equations. Okay, so if you look at this, you can see here I have 2 mole of hydrogen gas. No, I've already told you this is 1 mole, this is 2 mole. So from the equation itself, you can see that we have 2 mole of liquid water. And the problem said we should write for 1 mole of liquid water. What do you think we need to do to make it to be 1? Can you give me the result? What do you think that we can do to make this one to be 1 mole of liquid water? Yes, exactly. We have to divide all these equations by 2, or you can say multiply all the equation by half. Because the only thing we need to do here is to remove these 2. And to remove these 2, we have to divide all these equations by 2. So remember, we want to divide by 2. It must affect this. It must affect this. It must affect the energy level too as well. I hope you are following, right? So let's do that. Divide all the values, or you can say multiply all by half. It's still the same thing. If I multiply all by half, anyone you like, it's still the same thing. You can say multiply all through by half. How do I say half? This is 2. So 1 over 2 times 2, you see we are going to have 1. Is it clear? Or if you say divide all through by 2, then it's still going to be the same. So multiply all through by half, or divide all through by 2. Still the same thing. So the first one, that means that we have 1 over 2 times 2 for hydrogen gas. That's for the first one. The second one plus 1 over 2 oxygen gas. Now for this, that's going to be 1 over 2 multiplied by 2 H2O, which is liquid. So the moment you affect the numbers, it must affect the energy level as well. So the level of this as a half multiplied by minus 572 kilojoule per mole. Right? So now from here now, 2 can cancel 2 here. If 2 cancel 2, what do we have left here? We are going to have hydrogen gas. So you can see this one cannot cancel each other. So what I have here is a half oxygen gas. Now, from here to 2 can cancel 2. So if 2 cancel 2 here, you can see what we have left is a H2O, which is liquid. Then the energy level of this is now this is minus. So 572 divided by 2, I think that's going to be 286. So 2 in 5 is 2, 7. That's going to be 16. That is 8. Yeah, it's 286. So here we have minus 286 kilojoule per mole. You get that? Fine. But that's not the final. That's not the final result, because you said give the reverse in which 1 mole of liquid water dissociates into hydrogen and oxygen. So we have to reverse this one, meaning just like the way we do the first examples. What we have at the reactant, what we have at the reactant will go to the product. What we have at the product will come to the reactant. So if I do that here, so this will go here, the other one will go there. So that means there we have H2O, which is liquid, give hydrogen gas plus half oxygen gas. What are we doing there? We are reversing this. Then I told you, if the energy level, you're going to affect the energy level too as well. So what we have here is minus now. So the moment we reverse it, it's going to become plus 286 kilojoule per mole. So that's what we have for this particular problem. You can see that in reversing equations, it's just that what we have at the product, it goes to the reactant. what we have at the reactant will go to the product, and it will also affect the energy level. I hope you are following, right? Yeah, fine. So let's continue. We still have another one that we call, so you don't need to worry, I will explain all this one, the materials. I just want to go to calculation direct. We are going to talk about standard enthalpy change of solution, enthalpy change of neutralizations. So I just want to go to how to calculate standard enthalpy change of reactions. Standard enthalpy change of reactions. Standard So there, how to calculate that? It's just so simple. You just have to master the formulas. And we have already break down the moles. I told you the moles, because the mole too, it has a lot of effects. You just have to consider the one with so we call it, how can we calculate standard enthalpy, standard enthalpy change of a reaction. So that one is denoted by this. Standard enthalpy change of reactions. So this matters to what we have at the reactants and what we have at the product. So for example, let's say I have, let's say we have A plus B to give C plus D, for example. So if you are given, this is what we have at the reactant. This is what we have at the reactant. And here is what we have at the product. So if I want to obtain their standard enthalpy change, what I need to do, I will calculate total heat change at the product side. I will find total heat change at the reactant side, and I will find their difference. How? So standard enthalpy change of any reactions is given as change in heat of the product minus change in heat of the reactant. So how are we going to do that? It means if I'm given a problem, I'll find total heat change at the reactant, but mind you, what we have at their mole is very important. You see, don't worry, I'll solve like 2 examples so that you'll be able to understand better. So I'll find total heat change at the product, I'll find total heat change at the reactant. So their difference is what we call standard enthalpy change. Let's see examples. Let's see one example or 2 examples. I'll solve 2 so that you'll be able to have better understanding. They say calculate the enthalpy change for the reaction below. Calculate the enthalpy change for the reaction below. So let's see how we are going to do that. So we have C3H8 plus 5 oxygen gas to give 3 CO2, this gas, plus 4 H2O, which is liquid. And also given that function of this over C3H8, you say that one is minus 104 kilojoule per mole. Then for the water, that one is minus 286 kilojoule per mole. Then for CO2, which is carbon dioxide, that one is minus 394 kilojoule per mole. So we have to find the standard enthalpy change. It's simple and straightforward. So how will I do that? As I told you earlier, find the total heat change at the reactant. At the same time, find total heat change at the product. Then you now find their what? You find their difference. So how are we going to do that? This is our reactant side, and this is what we have on the product side, right? This is what we have the product. So now let's see how we are going to do that. So if I take it here, I have C3H8, which is gas, plus 5 over 2 oxygen gas. So this is the one I have at the reactant, right? So this is what we have at the reactant. So you can see the mole of this one is 1 because it's not 3 and it's not 8. Now I told you this is just a subscript. So this is what we have. We have 1 here, and here we have 5. I hope you are following the 5 that we have here. So let's find that it change at the reactant now. So from the problem, we are given this to be, look at it, C3H8, we are given it to be minus 104. That is minus 1, C3H8. Is it balance of the carbon? I want to see. So we are still going to have the materials for the organic chemistry. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, okay. 6, 7, 8. So I think that's going to be propane. So don't worry, you will enjoy us more for the organic chemistry. We are coming to that as well. So now, minus 104 plus 5. So for the oxygen, you can see in the values, we are not given the oxygen gas. So that one is 0. But the value is not given, it's not stated. So here we have minus 104. 5 times 0, we have 0. So minus 104 plus 0, of course, we are going to have minus 104 kilojoule per mole. Is it clear? Yeah, fine. So now the last one, we have to find, okay, we have gotten for the reactant. So let's see for the product. So for the product, changing it for the product, check what value do we have at the product side. What we have at the product side is 3 carbon 4 oxide, and at the same time we have 4 H2O. So I will still go the same way. You see what we have here is 3. That's going to be 3 bracket carbon 4 oxide. Can we see calculator? Okay, it's there. So carbon 4 oxide is look at the value we have, it to be minus 394 plus, this is 4. Can you see 4 for the beside water? This is 4 bracket of H2O is minus 286. Can we see that? So now, if I multiply 3, let's do that to make our work easier. 3 multiplied by 394, what I have here is I have minus 1182. So you can see this is plus, this is minus, plus times minus, and we have minus 4 multiplied by 286. We are going to have 114 and 4. So if I combine that one together, so what I have is minus 2326 kilojoule per mole. Can you see that? So I just combine them together. This is 3. So CO2 is minus 394 plus 4. H2O is minus 286. So minus 394, 3 times minus 394, I have minus 1182. Then plus times minus of this, I have minus 4 times 286, we are going to have 2326. So now we have gotten the one we have at the product, and we have gotten the one we have at the reactant. What's going to be the next step is to find the standard enthalpy change. So back to the formula we write earlier, standard enthalpy change is equal to change in heat of the product minus change in heat of the reactant. Please take note of that. It's not reactant minus product. It's change in heat of the product minus change in heat of the reactant. So here I can have, so what do we have at the product? What I have is minus 2326 minus, for the product, what I have there is minus 104. Can you see? Or at the reactant, rather, we have minus 104. This is a bracket of minus 104. So here we can have minus 2326 minus times minus, I can have plus 104. So now, let's do that. If you check that one, your result is going to be minus 2222 kilojoule per mole. Can you see that? Can you see that? So that's our standard enthalpy enthalpy change. Just find the one we have at the product, calculate the one we have at the reactant, then find their difference. So the difference is what we call standard enthalpy change. So let's see another problem. Look at these exercises from Federal University. Let's see these exercises. And Kuma, if you know, these things are also important for exam students that are preparing for exams. All these things is all in there. It's also simple and straightforward. So let's look at this. They said calculate the standard enthalpy change for the reaction we have calcium oxide plus H2O, which is liquid, calcium oxide. So they say given that the standard enthalpy change, the standard enthalpy change of formation of calcium oxide, water and calcium hydroxide are minus 635, minus 286 and minus 987 kilojoule per mole. So we are asked to calculate standard enthalpy change. You see the same thing. So the first thing, you find the one you have at the reactant. At the same time, you find that heat change at the product, then you calculate their difference. So the one we have at the reactant, let's firstly solve that one. For the reactant, we have calcium oxide plus H2O. So luckily for us, you can see this is just 1 mole. At the same time, this is also another 1 mole. So calcium oxide is, can you see from there? Calcium oxide is first value given, that is minus 635. Water is also minus 286. But we know if plus and minus come together, what are we going to have? Yeah, we are going to have minus. So here I can have minus 635 minus 286. So minus 635 minus 286. So this is 1. Then this is 3 plus 8 is 11 plus 1. We are going to have 12. This is 8. Then this is a minus 921. Minus 921 kilojoule per mole. So, but you can see for the product, we only have one value, Jacob, right? We only have calcium hydroxide there. And for the calcium hydroxide, we are different that the value of that one is minus 987 kilojoule per mole. So the next step is to find the total of standard enthalpy change for this. So standard enthalpy change for these reactions is going to be change in heat of the product minus change in heat of the reactant. So what we have at the product, we have it to be minus 987 minus, so what we have at the product at the reactant, we have it to be, what we have at the reactant, we have it to be minus 921. Can you see that? So now, this can just be minus 987. So minus times minus. Minus times minus, we are going to have plus, then we have 921. So 987, 921 So if I do that, I think we are going to have minus 66 kilojoule per mole. Can you see that? Yeah. So that's all about the standard enthalpy change. So there's another one. Let me add that one. We have Hess law, we have Haber cycle. So I'll treat Hess law. Then for the Haber cycle, once you check our materials, just so simple, just similar cases. But in case if you need that one, we can assist you. You can just subscribe, message us, then we will be able to find the solution to that. So now, but I'll just teach you a case of Hess law dealing with hydrocarbon. There's one formula that we normally use to balance hydrocarbon. Let me first do with that first. Before we go to Hess law. Then there's one general formula that we can use to balance, because most of the question under this Hess law and Haber cycle mostly enough. I will treat for the hydrocarbon now, then the rest is going to be in our materials. Or in case if you know that, you can kindly message us, then we find the solution to that one as well. So now, let's see. Let me give you one formula. There's one formula called this combustion, so that we used to balance any hydrocarbon. That is a CXHY plus X plus Y over 4 oxygen gas to give XCO2 plus Y over 2 water. You see this formula? It can be used to balance any hydrocarbon, especially when we have either being methane or being either alkane group, you understand, or alkane in terms of carbon and nitrogen like this. So how are we going to balance that? You know what I'm trying to tell us is that the subscript matters. The one we have for X, the one we have, so the subscript of carbon is X, the subscript for hydrogen is our Y. For example, let's say I want to write the general formula for C2H4. I want to balance equation for that. So let's see how we're going to do that. So meaning here, C2H4. So what does that mean here? That means my X is 2 and my Y is 4. Are you following? Let's put the formula. So that means that we have C2H4. I'm just substituting the values. Plus X is 2 again. Y is 4. This is 4 over 4. Oxygen gas. So X is 2 CO2. Y is 4. It's a 4 over 2 H2O. Can you see that? So here I can have C2H4 plus, you can see 4 over 4 is going to give us 1. So 2 plus 1, now we have 3 oxygen gas to give 2 CO2. So 2 in 4, we are going to have 2 H2O. So this is gas, this is gas, this is gas, and this is liquid. So let's check if the equation is balanced. So here I have 2 carbon. Let's check. I have 2 carbon here. Of course, I have 2 carbon here too as well. 4 hydrogen, 2 times 2. We are going to have 4 hydrogen, 6 oxygen. Then here 2 times 2 here, we have 4 oxygen, 2 here 2. So 4 plus 2, that's going to give us 6 oxygen. So that means what we have at the reactant, what we have at the product, balance. So in Hess law, what we normally do is we'll be reversing equations. You know, we already talked about how to reverse equations. At the same time, where it matters for us to multiply in the given expressions, we have to do that. So please just kindly follow, and you'll be able to understand the Hess law. The Haber cycle, I will put down in my materials. So far you get the concept of this. It has many methods of doing that, but I will just give you the simplest method. Hess law. We have what we call Hess law. So in this case, we deal with how to reverse equations. We do a lot of things. So now let's see. Is that the law, which is thermochemical function of the law of conversion of energy, was developed in 1840. So the law says that the enthalpy change of a reaction is the same whether it's occurred by one step or by series of steps. So let's see this one. They said calculate. I will give you, since you have done how to reverse equations, I will use the simplest method. For the reaction, given the following thermochemical equations. Okay, 2 carbon and solid plus hydrogen gas 13. So given the following thermochemical equations, the first one, C2H2, this gas, plus 5/2 oxygen gas. Then we have 2CO2, which is gas, plus H2O, which is a liquid. Then for this, we have the value of this to be minus 1299.6 kilojoule per mole. That's for the first one. This is equation 1. It was labeled as equation 1. Then the second one, they said carbon plus oxygen gas. Let's give us CO2. So this is labeled as second one to be minus 393.5 kilojoule per mole. Then the other one, hydrogen gas, that one too as well, is labeled as minus 285.8 kilojoule per mole. And then I said this is equation 2, this is equation 3. And then now said you find the changing energy level of this. So the target, you can see we have what we call target equations. Target equation means the one we have to find its changing it. This one. You see, we have 3 things there. Can you check? You can see we have 3 things there. So since we have 3 things, that's why we have 3 equation 2 as well. You can see 1. Maybe I just label them for you to see. This is 1, 2, and 3. You can see the equation is also 3, right? So in short, the one you are looking for, let me just give you a simple clue. We have many ways of doing this, but let me give you a simple clue. You will just be checking for the one related to the equations. If you look at this is carbon. You check between this equation, where do you have carbon? This is hydrogen gas, where do you have the hydrogen gas here? This is C2H2, where do you have C2H2 here? So let's consider for the first one. For carbon, can you check between the equation, where do we have carbon? Is it in equation 1? Equation 3? Yeah, equation 2, because if you look at equation 2, we have carbon there. So it meaning 2 carbon for equation 2 go, carbon for equation 2. So that will bring out our equation 2. What do we have in equation 2? Equation 2 is this. We have carbon solid plus oxygen gas gives CO2, which is also gas. The energy level of this is minus 393.5 kilojoule per mole. That's the first step. Let me repeat myself. The first thing, just consider the one you are looking for. So out of that 3 equations, there will be one that is related to it. So for the carbon, this is the one that is related to carbon, equation 2. Can you see where you have the carbon? So, but in the equations that we are looking for, how many carbon do we have there? We have 2 carbon, Abi? And here, how many carbon do we have? 1. Are they balanced? So what do we need to do? We need to multiply all this equation by 2. So if I multiply all this by 2, so 2 times 6. Why do we multiply by 2? Because in the one we are looking for, you can see we have 2 there. And here we have 1. So 2 times C, here we have 2 carbon solid. 2 times this, and we have 2 oxygen gas. 2 times CO2, and we have 2 CO2. Then here 2 times 6, and we have, if it will affect, just like the way we solved earlier, it must affect everything that we have in that equation. So 2 times, so multiply by 393.5, multiply by 2, 6, 10, 6, this is 7, this is 18, 10 plus, okay. This is 18, this is 6, this is 7, that is 7, minus 787. So let me confirm the result again. 393.5 multiply by 2, we have minus 787. We have minus 787 kilojoule per mole. Can you see that? Okay. So that means for the first one, we have got the result for the first one. So now, the second one we have is hydrogen gas. Oh yeah, let's check where we have the hydrogen gas in that equation. Where do we have it? Is it in equation 1? Equation 2? Yeah, equation 3, because hydrogen gas that we have is in equation 3 here. Can you see? Yeah, so that means hydrogen gas for equation 3, hydrogen gas for 3. So let's bring it out. So for that 3, we have hydrogen gas plus half oxygen gas give H2O, which is liquid. So this is a minus 285.8 kilojoule per mole. So there's one thing I need to mention. When you compare, you check where do we have it. If it is as a reactant, and the one you're looking for at the product, you need to reverse. But luckily for us in the first one, the carbon we have is the reactant side, and the one we are comparing with is also at the reactant side. And then if this is product side, I have to reverse until it comes to reactant side. So for the hydrogen gas now, where do we have it? Is it at the reactant side? Yes, the reactant side. And the one we are comparing with is also at the reactant side. Yeah. So now, how many hydrogen do we have here? You can see just like 2 sources of hydrogen, one more, then this one too. So you don't need to multiply anything by this one because it's balanced already. Are we there? So this is the first one. Let's label this one. This is for A, and this is for B. You can see I did not touch for this one because it's balanced already. I have hydrogen gas here, I have hydrogen gas here. The hydrogen I have is at the reactant side, the one I have here is also at the reactant side. So the last one is at 18. It is hydrogen gas for equation 3 equal. So now the last one is I think C2H2. So which equation is suitable for C2H2? Is it equation 1, 2, or 3? Check please. Which one? Yeah, it's equation 1. You can see that. So now okay, this one. And say C2H2 for equation 1. And what do we have in equation 1? Equation 1 stated that this is what we have there. We have C2H5, C2H2 rather, plus hydrogen, 5/2 oxygen gas produces 2 CO2 plus H2O, which is liquid. Then the energy level of this is minus 1299.6 kilojoule per mole. So if you look at this one, you can see the one we are looking for, we have it at where? Product side. But the one we are comparing, where do we have it? We have it at the reactant side. So what do we do? This is it. What do we need to do? We need to reverse it. Why do we need to reverse? Because the one we are looking for is at the product side, and this one is at the reactant side. So we have to reverse that one so that it will come to the product side. And recall the way we reverse. How do you manually reverse? What we have at the product side, we go to the reactant. What we have at the reactants, we go to the product, and the energy level will change. So now, if I reverse this one, so reverse. So this will go here, this will come here. So meaning that we have 2 CO2, the one we have here first, then plus H2O, which is liquid. So give this back. We have let me show this one. We have C2H2 plus 5/2 oxygen gas. I told you this one will for the energy level. So minus the first one equal to, this is minus, it comes to positive, plus 1299.6 kilojoule. Can you see that? Okay. So now we have got all the 3 now. We have done for the carbon, done for the waters, and we have done for the C2H2. So let them find the total heat involved now. is going to be the total of what we have. So unit now is equal to. So what do we get for the first one? See, what we get for the first one. Okay, let me just identify them. This is the first one. This is the second one. You know, all this one is after reverse code. So now the first one we have is minus 787. The second one we have is minus 285.8, and the third one is 1299.6. Even all are positive, you add them together. So let's see the result with calculator. The first one is minus 787 minus 285.8 plus 1299.6. So what I have here is 226.8 kilojoule per mole. So that's all we have for this thermochemistry. So please don't forget the Banama Circle to play that one in the materials. So please don't forget to like our videos, share so that others can be able. And in case if you have any questions, just can click because message or then we'll be able to reply your message. So thanks for watching. Please don't forget to like, subscribe, and share. Thanks for watching.